Okay, so this design over here is the crane. In this particular crane design, you're using the constraints that we have on the Google Classroom. What I've done here is I've already made the base plate, and this base plate over here is our 150 by 150 by 20 millimeters. That's like a profile, and this over here is 60 centimeters long, and this square over here represents the dimensions that we need our crane to lift. We need to go out by 300 millimeters, and we have to go up 300 millimeters. So we need to get our crane to hit this top point over here. So what I'm doing right now is I'm in my sketching, and I'm going to start by sketching the side profile of the crane. So let's go and pick a spot. I'm going to pick this spot over here. And from here, I want to go out at 45 degrees, and let's pick a spot closer. Let's go over here, and I want to go out at 45 degrees, and I want to, if I go out to there, that's going to be 497. So let's just say we go as a nice even half a meter. That is the size of the crane bit, and we see here that that's easily going to lift our object above 300 millimeters, and it's going to go past 300 millimeters, so we can use this as the general setup for our crane. And then what I'm going to do is I'm going to copy this. Can I move and copy? I will make I'm going to make another line, but first let's go to here. This should also be at 45 degrees. Let's just say, for simplicity of our cutting, let's make this 100 millimeters. All right, and then let's go, before we go down here, the one thing we have to do is we have to click this object down here, which is our base plate, and we want to include this so we can actually attach to this geometry. And now that we have that, we can go all the way down. It's going to attach to it. We want our thing here to be 135, which should be at 45 degrees, and then what happened there? Let's just fix that up again, please. So we have 50, 35 degrees. Okay, we're good. We're over here. Now we want to just continue our zigzag pattern. This will be the general structure of actually, we don't have to do the whole truss yet. For now, let's just leave this as our general crane shape. And then what we're going to do is we'll start by making our aluminium pieces along this. So, in fact, I think I want to delete this particular one there. I just want to have these two lines. I'm going to finish this sketch, and then I am going to start by making a construction plane. I want to make a plane along a path. So if I click this particular piece over here, I want this plane to be all the way at the end. This is so now I can sketch along this plane, and let me just hide the base. And I believe I'm sketching along over here. I'm going to make the shape of the aluminium tubing that we have access to. So the shape of it is basically something like this. Right, that's the general L shape, and we obviously have some dimensions, so we know that it is 12 by 12 by, this is going to be 1.4, and this over here is going to equal this. And that's our shape of our aluminium L shapes. Then we can simply get that shape, and we could extrude it, or we can also get it to sweep. And press this particular shape here. The path that we want to follow is this particular path over here, and that's going to be the start of our piece of aluminium. We might even want to later. Hold on. Later we'll fix up the base. but that's our particular piece of aluminium. And what we can do is we can, if we look at our sketch, I believe, not that sketch, this sketch. That sketch is going to have the other piece of aluminium we need as well. So how will we do that? We can do the same thing. We can construct, point along a path, same thing, okay. And when we do this sketch, we're going to do the same thing. We're going to make the same shape, except now this piece of aluminium we want it to be looking like in the other direction. Right, and we can make our life easier on us by, can we relate it to the other sketch? I think we can. I think we can say we want this length to be equal to this length. No, we can't, never mind. So we just have to do it manually. Escape. This over here is going to be 1.4. This one is going to be equal to this one. And same thing, we're going to get this and we're going to sweep it, this profile along this path, and press OK. We'll get half the crane done at the start. Now, I think we can cheat as we do the rest. See how I like this pattern over here? How what I'm going to do when I do this side profile now, what I'm going to do is I'm going to make a profile over here. I want to do all the cross members. So what I'm going to do for this is I'm going to I'm just going to do all the horizontal members for now. And we see here that it doesn't perfectly line up, but we'll deal with that later. We'll get something exotic at the top. So we have this. So what we're going to do, what's the best way to do this structure? We can either go and copy it. We should probably try and copy it because that does look nice if we do a copy. So let's go and finish this sketch. We want our things to line up that shape, so we can construct, pattern along a path, same thing, so we got that shape over there. When we draw over here, we're going to have the same shape that we've done for all our previous ones, where we're going to go over here and we're going to go get the shape and 12, and that's 12, 1.4, and 1.4. Finish sketch. Then we want to sweep this along this path, and now we don't want to cut this. Right? What we want to do is we want to make a new body. Right? And now notice here we're having some issues. Right? We are getting some overlaps. Right? So what we have to do here is we have this body, and we're going to move this body. It's going to be a realistic constraint we have to do. We're going to move this body some, I believe if we move it minus 1.4, right, it should at least match over here. But over here we have another issue where we're going to have to cut some parts out of this body because that doesn't it's not having fun. So what we're going to do is we will sketch this shape over here, and what we want to do is we want to project and include. We want to include this. We want to include this. Okay, and then we want to make a shape that's like this. Right, and if we make this particular shape, we're gonna, because in realistically when we make our thing, this is all gonna disappear. And then we can go through and we can cut, but we don't want, we only want this body to be cut. So we just do that, and then we press OK. And now if we bring all our other bodies back, ooh, did that work? Oh, that looks nice. We have to do the same thing there, but let's how much do I care about it? Sure, why not? I care about it a lot. Everything's important. We'll do the same thing over here, where we will just include this, include this geometry over here, and we're going to do the same thing where we're going to make we just need to delete that triangle, and then we're going to, this is one of those things that this over here would be incredibly easy to do in real life, because you just mesh it until it fits, or you file it until it fits. But over here we do this, and now we have a perfectly done piece. Now we've done all this effort, so I really don't want to have to draw and copy this multiple times. So what I'm going to do is I'm going to try and see if I can make a pattern. I want to see if I can make a pattern along a path. I think we've done this tool before when we're doing our lamps. So the object we want is this body over here. We want this body, and then the path, we have this lovely path over here. And now I think actually we can sort of cheat, in that we can just make this, we can visibly see how long we want it. So we make it up to 480, and then we can just choose how many members, because we know by our maths how many members we have available, and we can just do that. Right, and then we have that part of the structure. Okay, and ooh, that is looking nice. Now let's do our next part of our design, where we want to have this cross member. Now this member is going to be slightly different. So what I want to do is I want to sketch along a nice clean, can you please let me do that? Thank you. As a sketch over here, I want to make a point. I want to sketch between, I want a line that is basically between here and here. But I want this exact line. So what I'm going to do is I'm going to include all this geometry. I want this shape, and I want this shape in my geometry, because I want to get a perfect line that goes from here to here. Right, that's the line I want. That's all I want in my sketch, that particular line there. I then will go and do the same thing where I'm making a thing along a line, and we want it to be all the way over here. Yep. Then, so we will go and sketch this, and we're doing the same. We're doing the same shape that we did previously, where we go over here. Alright, doing the same thing we do there. We will sweep it along that particular line. The reason we're doing sweeping instead of extruding is because notice it will go the whole length there. We don't have to plug in the exact length that we want. But we do want this to be a new body. And like our previous, well, unlike our previous one, this one is being double overlapped. So we need to design this one. This one's going to be very weird. So we might have to cut it there twice, but how are we going to do that in real life? We might just have to put a washer there. All right, so this particular one, we will go and move this object. We want to move it this way, 1.4 plus times 2. All right. So it matches over here, so we can just drill that. We can drill this particular part there, and we can connect that like a truss in that location. The only issue we have here is we have this little gap over here. So what we're going to do is we will, how will we do this? We will have to make a connective piece there. So we will sketch over here. We will include this geometry. Yep. Can I press enter? Did it work? Alright, and then we just make a piece that goes from here to here. I hope that worked. And then we finish the sketch, and then we will extrude this. We will make this particular shape go until it, instead of distance, we're going to say to object. So we're going to say to that object over there, and it should make that. Now we want this to be join, but we don't. If we press join, it's going to join all these bodies together. We don't want that. We just want it to look like that. So this could simulate us putting like another piece of aluminium there to fix that issue, but this particular thing now should look nice. It's connected. Oh, where are you? Okay. That's a second piece of aluminium there, and we're going to do the same thing we did last time where we're going to clean this up. We don't need this base plate anymore. We're just going to clean this up by sketching this particular body, and we will include this. And can we do them all at once? It doesn't touch there, so that's fine, but it does touch, no, it doesn't touch anywhere else there. Okay, cool. So now we just got to make a shape that is just going to make a shape that covers these areas that are going to be cut out. And then we've done that sketches, and then we will go and hide everything else because we don't want to destroy the rest of our designs. We will go here and we will pick all these pieces that are overlapping, and we'll just cut them out, but I believe we have to do it through two sides. Okay, and we will also pick this for profiles, also pick that and that. I think that's it. Or this. That should be okay. If we press OK, we have that cut, and now we can show everything again. Alright, that's looking good. And we're going to do the same thing we did last time, where we're going to pattern along a path. We're going to pick this body. The path we're going to select could be this path this path over here. And the extent we want this one. Right, that means everything here should line up. And then how many copies do we want? We want, there we go. Over here we have a nice little truss structure. Now for this particular simulation and the time we have here, I could copy paste it, and do it the other side and then make some cross members. But for this particular one, I'm just going to leave it as a single one for our particular example. And we'll go with this. So let's try to actually get a simulation. Now the first thing we're going to do is save it. We'll save it as Truss simulation, save. Don't care about the material yet, but we'll get to that later. So let's go and go to design. Let's go to simulation and see what's happening here. What we want to try first doing a static stress study. So if we open up static stress, some bodies have interference, that's fine. Okay, so the first thing we have here, we have multiple bodies, right? So, and in our real life, we're going to drill those and connect them together. So what we're going to do here instead is we will go through and we have our study. We're going to, oh no, what did I press simplify? Go back, please. Done simplify. We want to go to contacts and we want to press automatic contacts. So anytime there is a solid that is within 0.1 millimeter, we're going to assume that they're connected together. Generate. Because we have all these individual planks, and what this is going to do, it's going to make all these assume that these are all connected. So now, and our material studies, everything here is steel, so we actually want to, can we change everything to, let's go back to our model, because I think it might be easier in our model for us to hide this, select all this, and then hide our sketches. Select all this, right click, physical material, and make this aluminium, which should be under metal, aluminium. Can I just, is that going to do the whole thing? Whole thing's aluminium? Lovely. Okay, save. Yep, save. Go back to our design, our simulation. So now we have, these are all aluminium. So if we look at our materials, these are all aluminium, except our base plate is steel, but in real life it's wood, but you can't really simulate wood. So we'll deal with that later. Constraints. So we have here a fixed constraint. Let's make our whole base plate is fixed. Right, so we won't worry about the counterweight for now. And let's put a load. So in this particular one, we're just going to put a structural load. We're just going to put a load of a force. And we're just going to assume in our very simple scenario that we're just going to put the force on this member over there, and we want it to go down in the X direction. So let's just say we want 20 kilos. That's going to be 200. Oh, no, I want wrong. Yeah, that's X. We don't want X. We want Y. Y to be minus 200. There we go, and we'll worry about the excuse me. If we have a pulley, we'll worry about the pulley later. I just want to see if we get any interesting results just by doing this. So we have this force going down by that, and let's go and see if we can get a, let's do a pre-check that has all the information required. So now let's go and solve it and see, or do I do it on my own computer? How long will it take? I don't want cloud credits. Let's see if my computer's faster. I don't want to, well, now I have to install a software. It's more than I thought. No, go away. Let's just do it on the cloud. I have unlimited things anyway. Alright, I'm going to go pause my video while I can explain what's happening here. Alright, so we've done our truss simulation over here. If we go back, oh, you know what? Weird flex, but okay. We have over here our, we have our So this over here, right? First thing, it looks terrible, but keep in mind they always show the deformation. It's always adjusted, right? The deformation in Fusion 360 is adjusted, so you can it's like exaggerating the deformation if it's too small, or if it's ridiculous, it's scaling it down. So the point is, you can generally see what the deformation would look like. If you put actual, it's like realistically it's nothing. But it's usually adjusted is usually just a good indication of adjusted times 5. Meow. It's like a fishing rod. Adjusted is just a way for you to visually understand what the material is doing right now. Like this little piece over here, we know this is having a force here, that this is bending, so we can get some sort of understanding, or this particular area over here is like under a torsion. Next thing we have, in Fusion 360 by default, it has this thing called a load case, which factor of safety is, remember how we did our shear force and our shear stress situations in our previous lessons? What it's saying over here is this piece of aluminium structure under the particular loads that we gave it, its factor of safety is 2.8, which means with this particular forces that we're putting on the structure, it is less than it's the ultimate tensile strength of aluminium is at least 2.8 times more than the force it's experiencing. So it shouldn't break. But this is also a simplified scenario because we don't have the holes where we're going to be putting our rivets or our bolts and stuff like that. So what we can also do is we can also look at our stress. And if we can see our stress over here, we can see areas where we are more likely to have an issue. If we see over here, the maximum stress is this particular part over here. This particular area over here has the maximum stress of 98 megapascals. And so I think we had aluminium somewhere near that, I believe. That's where our maximum stress happens. We can also change our load case for our displacement. This is absolute displacement, so obviously the very tip over here is going to be where the most of the displacement is. We can also change our reaction forces are going to be down here on the base plate, and so we can see where the maximum reaction force. Now this is assuming the whole thing is the whole base plate is just one solid thing. We see we have the most reaction force down here. And if you do your maths and your calculations, if you look at that, it's approximately like where the bottom of this is. So that you should see if you should be getting like some sort of similar numbers. But isn't it interesting how the two reaction forces here and here make sense to if we were to do this in truss analysis? They relate to like the base of that. What else do we have? Strain, which is well, we learned about stress, and strain is like movement. Contact pressure, I believe that's see how these are joints over here. It's showing what the connection force is. This is if you, for example, think of this, if you were gluing objects together, saying if I was gluing these two objects together, how much force would that glue have to be able to withstand? And if we see here, the maximum we have is 6.5. So the most glue would be needed, well, over here, it doesn't make sense, but like over here we can see that it would need about 15, megapascals, so whatever that means. So we have that. So let's see. We plan on doing our things by rivets. Rivets are made out of the same metal as aluminium, but what they do is they do make a hole. So I'll do a test later showing a rivet. So let's say I want to actually change this result because this has a weird twist. I want to change that twist. When I do my force, when I look at my loads, this particular load over here, well, okay, it's on a hole. Instead of it being on an edge, I want it to be, let's say I want it to be right over, I want it to be right on this point over here. Right on the edge because I don't want it to do that twisting motion. And then let's say instead of 20 kilos, let's say we do 50 kilos. All right, you're going a big case over here. 50 kilos, let's see if anything is interesting happening over here. And we'll do the same thing is we'll solve this and we'll see if this solution goes through. And we'll see how long this one takes. Alright, so we have finished this case. In this case over here we put 50 kilos. Now, over here we're looking at approximately the limit that our single piece of aluminium, our single truss of aluminium can handle. We press close over here. If we look at our factor of safety, we're already at 1.143, which means using these solid pieces of aluminium, as in, notice how these don't have any holes in them, they're perfect. We're at like the limit of 1.4, which means our force is 1 over 1.14 of the limit of aluminium. So the point is, once we get to 1, the piece will break. Does that make sense? If you have a factor of safety of 10, it means your material is 10 times stronger than the maximum force. Because we're 1.14, our material is only 1.14 times stronger than the maximum force. So when we start drilling our holes are going to make it weaker. And in fact, I'll add it to the scenario. In fact, if this member over here, which is the 1, 2, 3, this member, I'll actually drill a hole there, and we'll see what happens with our design if that changes. Then our deformation is adjusted. If we look at the actual, we might be able to actually see some flex over here. We could look at when we do our real practical design, we could see over here the minimum flex we have is, that's factor of safety, sorry. When we do our flex, we can see actually how much our thing is changing, and we can measure it to see if our thing was statistically accurate. Hold on. We see here we're getting some, the whole thing is starting to buckle, it's starting to twist as well. And then our base reaction, let's look at our stress. 240 megapascals, so that's the strongest location right over there. Our reaction forces, 760. And remember, your design is going to be like a 3-dimensional one, so you're going to make it in like a square. This is just a particular line, so your one should still be stronger than this. Strain, contact pressure, all that other good stuff. The last thing I want to do is let's just look at this scenario over here, where this was a factor of safety of 1.1. I'm going to drill a hole there, and that hole is going to represent the rivet that is going to be connecting this particular truss together. So let's go back to our design. And let's just assume a worst case scenario. We're just going to drill this hole over here. All right. So our rivets are, I'm just going to guess them. Let's just say they're 2mm rivets. And in this particular one, I'm hiding all my sketches. All right. And this particular one is just going to go through. It is just going to go through everything. But when I cut you, you're going to join all these things together. I really hope you don't. Okay, good. So let's just say this over here is the hole that's going to connect those together, and then we will have a bolt that goes in there that connects it. The bolts the bolt will provide some sort of a supportive force linking these together, but let's just try it without it for now. So let's save this design, and let's say with riv. And now let's go to our simulation, and we're going to do the same test again. Let's go back to finish results. We have everything exactly the same. Let's go and solve this particular one over here. Solve. Oh, hold on. It has to redo its mesh. Because we changed the design, we have to redo our... it's saying these have to be redone. Our study, we don't have to simplify. We can see here the mesh that is simulating it, but I think we have to make a new mesh. We have to go to simplify environment. How do I do this again? Mesh is not up to date with current settings. Yeah, I'm aware of that. Uh, can we update? Can we update that sketch, please? Why are you not working with me? Was that an old load case? Create a new study. Let's just try if we just make a new study. Study 2. Okay. This one over here should have. Yes, I would like to make a mesh. So a mesh is the mathematical equation that they are running the simulation on. It's supposed to simplify it to some extent, and it's basically simplifying it down into triangles. And this particular mesh over here has to make these holes over here. We have our contacts. I think we have to make all our contacts again. Yes, generate. We have to make our constraints. We want our base to be fixed. And I believe our last one, to make it exactly the same, we want it to be a load going down, and it was this point over here, and it was minus 500. And then let's just do our pre-check. Right, everything's done. Solve. So we're going to see what the issue of having in a we can't redo that one. Yep, cancel. We just want study 2. Okay. Whatever, Fusion. So I'm expecting, this over here was our weakest point in our last one, and now that we also drilled a hole, we should be seeing that it might actually fail now at this point. It might be too much stress at this particular point that it's actually going to start to fail. So we could predict that if we made this particular lifting device in our classroom, that it's going to fail at this particular location. Right, so we're done. Over here we see load case. Firstly, it gives you a big red exclamation mark over here. Well, it's tiny compared to the screen, but it does say over here, actual minimum safety factor is 0.6. So it says its design is expected to bend permanently or break under the current structural analysis. It's warning you, don't make a bridge like this, it will fail. But this is expected since we know, well, this is what is assumed. Notice over here how this hole is now a square. Right? That's just because when it was simulating it, when it did the meshes, it simplified that circle as a square. So you could get a more accurate result if you change your mesh size, but for our particular scenarios, it's not really that relevant. The main thing is we know this part over here has 0.69, so over here, this particular support beam over here, that's what this one is connected to, we're expecting this to fail. Right? It's too much, it's going to start making a crack or something that will be the part of the bridge where it fails. And then there's going to be holes in other locations. So if I assume when we get the other side, because once we get the other side of the bridge as well, we know it's not going to be 50 kilos, it's actually going to be like 25 for each part of the structure, but it adds up. You can predict which is the area that is going to need some more support, even though yeah, there's going to be more compression for the motor and the pulley, and it's actually even slightly different because the scenario is slightly different because can I make a new one? Because the actual scenario we have is we have a base plate over here. Let's say we have a base plate over here, and we have another plate. We have another plate over here, and this particular one is coming out like this. This over here is a new body. And these over here have a hole over here connecting them. So we are going to, how is the best way to do this? We'll just extrude this and we'll make a new. And then we'll go and we will make a third body. And this over here is a new body. Okay, so we have 3. This is basically what our situation is going to look like, where we have our pop rivet in the middle, and it's going to be connecting these two. In fact, just for the sake, let me make it larger, just so we can. Oh no. Let me make it larger just so we can visibly see what's happening here. It's going to help us maybe get some more understanding. So this is over here, like our rivet that is sticking out. And if we go and save this as a riveting. If we do our riveting example over here, static stress, yep, sure. This particular, oh no, no. Go back to my design, please. No, how did this happen? Yeah, oh, it's all connected together. No. All the way back here, please. Right, then, so I have to do this again. Ugh. Like, why does this happen to me? Alright, so now, clearly I have to do this manually, and then this has to go out through here. 5, and this has to be a new body. Okay, now we have 3 bodies. Okay, that's what we need. Right, save. Design. Simulation. Alright, 3 bodies. Alright, cool. Now when we do our contacts here, we want to do manual contacts because do you want to generate automatic contacts? No. Okay, so we don't want these 2 bodies to be connected together because they actually are not connected together. They're not glued together in the actual objects. So what we're going to do is I'm going to make this the primary object, and you don't have to do this particular one. I just want to demonstrate. I just want to demonstrate what's going to happen. There's going to be a secondary body, and I believe we do section 1, and we do section 2, and then we say these can be bonded. Yes, they can be bonded together. Okay. And then contact, manual contact. We want this to be the primary body and this to be the secondary body, and we want this. So what I'm saying is these particular bodies are only connected by that particular part. So these 2 are not connected. So now, if I show a case over here where I say constraints, and I want this to be 1, and let's say we have a load. Oh, no, not 2 faces. Just 1 face, please. Thank you. And let's just get that load of we have just 500 newtons now. I believe. Do we have everything here? All setup is required. This should be faster to solve now. Solve. This riveting example should be faster, and we don't need equal. We don't need it because we have our constraint over here. Yeah. So what we're doing in this example, just before the bell rings, is demonstrating what's going to happen. So let's ignore our factor of safety and just look at our stress, and we see where is most of the stress is located right where the hole is. And in fact, if we hide these 2 bodies, we can see most of the stress is happening on here. This is the pin. This is where the stress is going to be connected together. So that's actually what's happening in our case, is we have that pin is where that force is going to be transferred to. Now, I don't know an easy way that you can set up in your design. If I find an easy way, I'll show you later. But for now, that's just yeah, it's buckling because it's in a weird case. But the force has to be transferred through the pin. That's it for this tutorial. I'm just going to end it now so I can save it. Where to show you how to build a truss and do some simulations for it.